In the vast silence of the solar system, where light travels for hours before touching the cold surfaces of distant worlds, there exist objects so small and so insignificant in appearance that most telescopes barely acknowledge their presence. These are the asteroids, relics of creation, fragments of rock and ice left behind from a time when the planets were only beginning to form. For centuries, asteroids were understood as primitive, simple bodies. They were believed to be barren, irregular, lifeless, and almost entirely predictable. They had no atmospheres. They had no magnetic fields. They had no geological activity. And they certainly had no rings. Rings belonged to giant mighty worlds like Saturn, Jupiter, Uranus, and Neptune, whose immense gravity could leash billions of icy particles into majestic, swirling disks. The idea that one of the smallest objects in the solar system could host its own ring system was considered not only unlikely, but physically impossible. It violated models, expectations, and the very structure of conventional astronomy. Yet this belief was shattered in 2013 when astronomers made a discovery so unexpected that it forced the scientific world to rewrite what was thought to be known about the small bodies of the solar system. They found a ring, not around a planet, not around a giant world, but around an asteroid. And not just one ring, two. Perfect, fragile, organized rings encircling an object no larger than a small mountain range on Earth. The discovery was nothing short of revolutionary. It was a whisper from the early solar system, revealing that the cosmos still held secrets in places no one thought to look. What made this revelation even more astonishing was the identity of the object itself. It was not a planet. It was not even a dwarf planet. It was a centaur, a strange class of small, unstable bodies that wander between the orbits of Saturn and Uranus. The centaur, carrying this miracle of nature, was named Chariklo, and its existence demanded a new chapter in our understanding of cosmic evolution. Astronomers had always believed that only massive objects with powerful gravitational fields could maintain rings. Yet Chariklo, barely 250 kilometers wide, had defied this rule. It was not supposed to be possible, but there was an asteroid with rings. Impossible, yet real. This documentary explores the full journey of this discovery from the moment Chariklo was first detected, to the stellar event that revealed its rings, to the theories that attempt to explain how such a tiny world could create and maintain one of the most delicate structures in the solar system. Through Chariklo, we glimpse the mysteries of the early solar system, the forces that shape the planets, and the hidden beauty that still exists in the most unexpected corners of the universe. This is the story of the asteroid with rings. It is a story of scientific shock, cosmic elegance, and a reminder that space still holds wonders capable of rewriting everything we know. For most of its existence, Chariklo drifted unnoticed in the cold darkness of the solar system. It had no atmosphere to reflect light in interesting ways. It had no volcanic activity, no geological features, and no dramatic behavior that would make it stand out to astronomers. It was, by all expectations, just another wandering rock among countless millions. Discovered in 1997, Chariklo was classified among the centaurs, a group of small bodies orbiting between Jupiter and Neptune. These objects are known for their instability. Their orbits are chaotic, influenced by the gravitational pull of the giant planets they pass. Centaurs often come from the Kuiper Belt, the frozen frontier beyond Neptune, and over millions of years they drift inward, eventually being captured, perturbed, or ejected from the solar system entirely. Chariklo's orbit placed it between Saturn and Uranus. It was bathed in weak sunlight, illuminated only by the faint glow, reflecting off the ice and dust grains drifting in the distant regions of space. It was assumed to be unremarkable quiet, irregular chunk of rock and ice, living out a lonely existence in the outer reaches of the solar system. Nothing about Chariklo suggested it could host a ring system. If anything, its weak gravity seemed incapable of holding even a temporary cloud of debris. Any material surrounding such a small object was expected to disperse quickly or collapse onto its surface. Rings, in the astronomical sense, require stability. They require balance between gravitational pull and orbital velocity. They require a delicate harmony between countless particles. And harmony was the last thing scientists expected from an object as small and irregular as Chariklo. Yet nature has a way of defying expectations. It does not conform to human assumptions. It does not obey the limits set by textbooks. Even the smallest worlds can carry hidden stories, waiting for the right moment to reveal themselves. Chariklo's moment of revelation came in 2013, during a rare and fleeting astronomical event that would transform it from an ordinary centaur into a cosmic anomaly. This event was a stellar occultation, a moment when Chariklo passed in front of a distant star, briefly blocking its light. Occultations are powerful tools for astronomers. They can reveal details about objects too small or too distant to study directly. The way a star's light dims, flickers, or disappears during an occultation provides clues about the shape, size, and even atmosphere of the object passing in front of it. For a small asteroid like Chariklo, an occultation should have been uneventful. The star's light would dim only once, precisely when Chariklo crossed it. There should have been no other interruptions, no additional dips in brightness. Yet what astronomers observed that night was anything but ordinary. Moments before Chariklo blocked the star, the light dipped twice. Then after Chariklo passed, it dipped twice again. For dips. 2 before, 2 after. The only explanation was that something else, too thin, circular structures surrounded Chariklo. And those structures were rings. Astronomers stared at the data in disbelief. The shape of the dips, the timing, the symmetry, everything pointed to the same conclusion. Chariklo, a tiny world with barely enough gravity to hold itself together, possessed a ring system. It was the smallest known object in the solar system to do so. The discovery seemed impossible, but the evidence was undeniable. The rings were real. The night Chariklo revealed its rings began quietly, without any expectation of scientific upheaval. Astronomers around the world were preparing for a simple stellar occultation, the kind they had observed hundreds of times before. These events require careful timing and precise coordination, because the alignment must be perfect. A distant star, billions of kilometers away, must fall exactly along the line of sight between Earth and a small object drifting through space. The window for such alignments lasts only seconds, sometimes fractions of a second. Miss the moment, and the chance is gone forever. Chariklo, at the time, was only a faint dot of moving light in the darkness. It had no distinguishing features, no intriguing behavior, and no reason for astronomers to expect anything unusual. Yet the occultation was still worth observing. By studying the way Chariklo interrupted the light of the star behind it, astronomers hoped to refine its size, shape, and orbital path. Nothing more. Nothing spectacular. Nothing revolutionary. The telescopes were ready. The star was bright enough to serve as a good measurement source. The observers were prepared to record the moment when Chariklo would pass in front of it, creating a predictable drop in brightness that would last only a few seconds. Everything was set. Then the unexpected happened. As the star's light approached the moment of occultation, observers noticed something unusual. The light dipped briefly, sharply, but unmistakably before Chariklo had even reached the star. This alone was strange. But before anyone could process what had happened, there was a second dip. 2 sudden dimmings of light, spaced perfectly apart, occurring before the asteroid had made contact with the star's line of sight. Observers were stunned. There was no reason for a small asteroid, one with no atmosphere, no known debris field, and no known moon to cause such behavior. Yet the data was being recorded in real time, clear and sharp. The star dimmed twice. Then Chariklo passed in front of it, creating the expected main dip. And as the asteroid moved away, the star dipped twice again. This symmetry was impossible to ignore. It was too clean, too precise, too perfect. Something circular, something organized, Something orbiting Chiricahua had crossed in front of the star before and after the body itself. Astronomers began to realize what they were seeing, and many of them did not believe it at first. Rings around an asteroid. The idea sounded absurd. Rings required stability and gravitational power. Rings required mass. Rings required structure. Chiricahua had none of these things. Yet the data presented the truth with stark clarity. Two rings. Two distinct, narrow rings. Structures so thin and so delicate that they could only have been detected through a stellar occultation. They had been invisible to telescopes before this night. They might have remained invisible for decades more had the alignment not occurred at this exact moment. Astronomers ran calculations immediately. The dips matched the model of narrow rings composed of ice and dust. The distance between the rings was consistent with gravity holding the particles in separate bands. Even the thickness of the rings could be estimated by the sharpness of the light interruption. Everything aligned. Everything made sense. Everything pointed to the same unbelievable conclusion. Chiricahua was the smallest ringed object ever discovered. The data was verified by multiple observatories across South America. The dips were recorded independently, at different altitudes, through different atmospheric conditions, yet the results were identical. This was not an error. This was not a glitch. This was real. The asteroid had rings. News of the discovery spread through the astronomical community with a mixture of excitement, confusion, and disbelief. Scientists who had spent decades studying the outer solar system began re-examining their assumptions. If an asteroid as small as Chiricahua could have rings, then what other small bodies might also host similar structures? How many were overlooked simply because no one expected them to exist? The night of the occultation changed more than just Chiricahua's classification. It changed the boundaries of what was possible in the solar system. It reminded astronomers that even the smallest, most unremarkable worlds could harbor secrets capable of reshaping scientific knowledge. And it set in motion a wave of new questions about the origin of Chiricahua's rings, their stability, their age, and their future. No one had imagined that a world so small could carry something so beautiful, fragile, and complex. Yet Chiricahua had done exactly that. In the darkness beyond Saturn, an impossible object drifted quietly through space, carrying rings like a miniature Saturn, silent, elegant, and hidden in the cold. The impossible had been seen. The real work of understanding it was only beginning. The discovery of Chiricahua's rings did more than surprise astronomers. It forced them to confront a question that struck at the heart of planetary science. How could such a tiny object maintain a ring system at all? Rings are complex structures. They require balance. They require a careful interplay of gravitational attraction, orbital speed, and stability across millions of particles. On a giant planet like Saturn, whose mass is immense, the existence of rings makes sense. Saturn's gravity can shepherd billions of icy particles into thin, stable bands. But Chiricahua was different. It was small, almost unbelievably small, compared to every ringed planet known before it. Its gravity was weak, barely strong enough to hold a loose collection of surface material. In theory, any debris around Chiricahua should either collapse onto its surface or drift away into space. The idea of rings seemed physically incompatible with its size. Yet the rings existed. They were measured. They were confirmed. They were mathematically consistent. And so the scientific community was forced to revisit their assumptions about gravity, debris dynamics, and the behavior of small bodies in the outer solar system. The first question was deceptively simple. How strong does gravity need to be to maintain a ring? Traditional models assumed a threshold that only planets or large moons could reach. But Chiricahua challenged this. Despite being tiny, it had enough gravitational influence to keep two thin rings in orbit. This meant the threshold was lower than previously believed, or that some special mechanism was helping Chiricahua maintain its rings. Scientists considered the rosette-like patterns observed in some ring systems, caused by shepherd moons, small natural satellites that orbit near the edges of rings and keep them narrow and organized. Saturn, for example, has several shepherd moons that maintain the crisp boundaries of its narrow rings. Could Chariklo have a similar mechanism? Could it host a tiny moon, or even multiple moons, too small to detect? This became one of the leading theories. A shepherd moon, even one only a few kilometers wide, could help maintain the structure and stability of Chariklo's rings. It could herd the particles, preventing them from spreading out or crashing into the asteroid. It would explain the surprising sharpness of the rings, the consistency of their separation, and the fact that they had survived long enough for astronomers to observe. But no such moon has ever been directly observed. If one exists, it is far too small for Earth-based telescopes to detect. Its presence remains hypothetical, inferred from the behavior of the rings rather than confirmed through direct observation. Another theory suggested that the rings might be temporary, short-lived, fragile structures that will eventually collapse on a Chariklo or disperse into space. In this model, the rings are not ancient relics from Chariklo's birth, but recent formations created by some relatively modern event, such as a collision. If a small moon or fragment had struck Chariklo in the past million years, the debris from the impact could have formed rings. Over time, the finer particles might spread out, thin, or dissipate, while the more stable chunks could remain in orbit for hundreds of thousands of years. If the rings are young, their existence becomes less difficult to explain. They would not have needed to remain stable for billions of years, only long enough for humans to observe them. Still, other theories propose something more dynamic. The rings might be forming and dissolving in cycles. Chariklo's orbit is not static. It moves through regions of space where gravitational influences from Saturn, Uranus, and even smaller bodies can affect its behavior. Perhaps the rings are periodically created by tidal forces or interactions with other centaurs. In this model, Chariklo's rings could be part of a repeating pattern of creation and destruction, a fragile equilibrium between chaos and order. Each theory had strengths and weaknesses. None were definitive, but they all shared a common theme. Chariklo had revealed that small bodies are more complex than once believed. For decades, astronomers thought that objects under a certain size were too weak, too simple, or too primitive to sustain ring systems. Chariklo proved that the universe does not obey human assumptions. Even the smallest objects can host structures of incredible beauty and complexity, given the right conditions. Chariklo also forced scientists to rethink the definition of what qualifies as a planet-like behavior. If rings had once been considered exclusive to large planets, the discovery suggested that ring formation is a more universal process. It might occur whenever debris, gravity, and orbital velocity fall into a precise alignment, regardless of whether the central body is large or small. This raised new possibilities. Could other centaurs have rings? Could asteroids in the main belt host similar systems? Could ring formation be a common stage in the life cycles of certain small bodies? The implications were profound. Chariklo was not merely an oddity, it was a clue. A sign that the outer solar system holds secrets still unseen, waiting in the cold darkness for the rare moments when they reveal themselves. The discovery pushed astronomers to search for signs of rings around other small bodies. The techniques used to discover Chariklo's rings, especially stellar occultation, became essential tools in this quest. If Chariklo could surprise the world, perhaps others would do the same. The rules of gravity had not changed, but humanity's understanding of them had. Chariklo stood as proof that the cosmos still had room to astonish. To understand the magnitude of Chariklo's discovery, we must examine the rings themselves, what they are made of, how wide they are, how close they orbit, and how such a delicate system could survive in the harsh environment of the outer solar system. At first glance, Chariklo's rings seem impossibly thin and impossibly precise. They are not chaotic clouds of dust. They are not loose, drifting streams of debris. They are organized structures, narrow and sharply defined, reminiscent of the more famous ring systems that encircle giant planets, To find such precision around such a small world was one of the greatest shocks produced by the discovery. The larger of the two rings, known informally as Ring 1, is approximately 7 kilometers wide. The second, Ring 2, is even narrower, only a few kilometers across. The distance between the rings is only about 9 kilometers, an extremely small separation in astronomical terms. Their orbit around Chariklo lies roughly 400 kilometers from its center. Because the asteroid itself is only about 250 kilometers wide, the rings orbit at a distance roughly twice the diameter of the central body. This proportion is unique in the solar system. Saturn's rings, by contrast, begin just above its atmosphere, and their width extends for tens of thousands of kilometers. Yet proportionally, Chariklo's rings are surprisingly similar in their tightness and structure. What makes the rings even more fascinating is their composition. Based on the way they reflect light during occultation events, scientists believe the rings are made primarily of water ice mixed with dusty material. This is remarkably similar to the composition of Saturn's rings, which are dominated by ice particles ranging from microscopic grains to chunks several meters wide. Chariklo's rings likely include a similar range of particle sizes, although the full distribution remains unknown. The presence of ice is significant because it suggests that Chariklo originated or spent much of its early life in a region of the solar system where water ice was common. This is consistent with the idea that many centaurs come from the Kuiper Belt, where icy materials dominate the population of small bodies. The shape of the rings also holds clues to their origin. They are not thick, diffuse structures. Instead, they are sharply confined, as though some invisible force is keeping them in place. This sharpness is one of the reasons astronomers believe a shepherd moon, or multiple shepherd moons, may be controlling the edges of the rings. On Saturn, shepherd moons like Prometheus and Pandora carve clear boundaries in the rings, preventing material from drifting away. If Chariklo hosts such moons, they must be incredibly small, no more than a few kilometers wide. Yet, even a moon this tiny could exert enough gravity to maintain the tight shape of the rings. Another striking feature of the rings is the degree of symmetry. Even though Chariklo is not a perfect sphere and likely has an irregular, elongated shape, the rings appear remarkably circular. This suggests that Chariklo's gravitational field, although weak, is symmetrical enough on average to maintain a stable orbital path for the particles. If Chariklo were too irregular, the rings would warp or wobble noticeably over time. Their current stability implies that Chariklo, despite its classification as an asteroid-like body, may be closer to hydrostatic equilibrium than previously assumed. In other words, it may be more rounded than many asteroids of similar size. The rings also appear to be extremely thin, so thin, in fact, that they become nearly invisible except during an occultation. Their vertical thickness is likely no more than a few tens of meters. This razor-thin structure raises another question. How have the particles avoided colliding and spreading out vertically? On larger worlds, vertical confinement is often maintained through gravitational resonances, interactions with moonlets, or complex orbital patterns. On Chariklo, with its limited gravitational influence, these mechanisms must operate on a much smaller scale. The stability of the rings suggests that whatever process governs their shape is both efficient and persistent. One theory proposes that collisions among ring particles occur frequently, but at extremely low speeds, just enough to dampen vertical motion, keeping them in a flat disk. The icy composition of the particles may also play a role. Ice is more elastic than rock, allowing particles to gently rebound rather than shatter. This could help maintain the ring's structure over long periods of time. Another factor is the environment of the outer solar system itself. Chariklo orbits in a region where sunlight is weak, temperatures are extremely low, and radiation pressure is minimal. These conditions reduce the forces that might otherwise erode the rings or push particles out of orbit. In the cold darkness beyond Saturn, even fragile structures can survive longer than expected. Yet despite their apparent stability, Chiricah's rings remain vulnerable. A passing object, even a small one, could disrupt them. A shift in Chiricah's orbit could destabilize the fragile balance that holds the particles in place. Over millions of years, gravitational interactions with Saturn or Uranus could stretch or twist the rings beyond recognition. Their long-term survival is uncertain. Still, for now, they endure. They drift silently around their small world, reflecting the faint sunlight that reaches them. They serve as a reminder that complexity exists even in the least expected places. Chiricah's rings may be miniature in size, but they are magnificent in significance. They are proof that beauty in the solar system is not limited to the giants. It exists everywhere, even around a lonely ice-covered rock in the darkness of space. The question of how Chiricah acquired its rings may be one of the most fascinating mysteries in modern planetary science. Unlike Saturn's rings, which are believed to be ancient and enormous, Chiricah's rings are tiny, young, and fragile. They do not appear to be billions of years old. They do not seem to be remnants from the early solar system. Instead, everything about them points to a more recent, dynamic origin, one tied to violent encounters, cosmic accidents, and the chaotic nature of the centaur population. One of the leading theories proposes that Chiricah once possessed a small moon, perhaps only a few kilometers in diameter, that ventured too close to its parent body. In this scenario, Chiricah's weak gravity and irregular shape created tidal forces strong enough to tear the moon apart. Over time, the debris from the shattered moon spread into a thin disk, eventually forming the two distinct rings seen today. This process mirrors, in miniature, the event that astronomers believe created Saturn's rings, a once stable moon stretched and shattered by gravitational forces, reduced to a halo of icy remnants. Another theory suggests a collision. If Chiricah were struck by a smaller rock while wandering between Saturn and Uranus, the impact could have created a cascade of icy debris. Unlike rocky asteroids in the inner solar system, centaurs contain significant amounts of frozen water. When hit, they do not simply crack, they explode into clouds of shimmering frost. These frozen fragments could have entered orbit instead of dispersing into space. Over time, collisions among the particles would have smoothed the debris into a thin sheet, eventually settling into the two elegant rings we observe today. There is also the possibility of cryovolcanism, a process known to occur on icy moons such as Enceladus. Although it is difficult to imagine an object as small as Chiricah producing volcanic activity, some researchers have speculated that internal stresses created by gravitational interactions with giant planets could cause eruptions of water vapor or ice crystals. These eruptions, once released, could form a temporary ring system. If such eruptions occurred repeatedly, the rings might be continually replenished, creating the appearance of long-term stability. But perhaps the most intriguing theory of all is the idea that Chiricah's rings are not static, they are evolutionary. They may be the remains of a larger system that has slowly eroded or faded over time. What we see now could be the quiet, dying echo of a once larger, more dynamic halo. Regardless of their origin, the rings tell a story of survival. They are proof that even the smallest bodies can undergo dramatic transformations. They show that the solar system is still alive, still sculpting new structures, still reshaping its fragments billions of years after its birth. And they serve as a reminder that even the quietest objects carry histories written in ice. The revelation that such a small world could host rings prompted astronomers to look outward with renewed curiosity. If Chiricah had rings, perhaps others did as well. Perhaps rings were not the trademark of giants, but a universal possibility, a structure that could form wherever certain conditions aligned. The next major milestone came when scientists discovered that another centaur, Chiron, exhibited behavior that hinted at a ring-like structure. Chiron, larger than Chiricah but still far too small to be considered a planet, showed brightness variations that could be explained by arcs or partial rings. Although its system is less well-defined and still debated, The very possibility that two centaurs could harbor ring structures redefined expectations. Suddenly, the outer solar system did not seem like an empty, frigid void filled with rocks and ice. It seemed alive with possibilities: fragile disks, temporary halos, and miniature systems orbiting small, wandering worlds. The giants no longer held a monopoly on cosmic beauty. This new understanding also cast fresh light on the formation of planets. Rings, once thought to be rare, might be common stages in the life cycles of many objects. Just as planets formed from rings of dust around the young sun, small bodies may form their own mini-disks following collisions or gravitational interactions. These rings, though small and temporary, could represent snapshots of the same processes that shaped the early solar system. Rings are laboratories of creation. They are arenas where particles interact, collide, merge, and sometimes form larger bodies. On Chariklo, those processes may be frozen in time, too fragile and too slow to build moons, but active enough to create a shimmering halo of icy debris. The implication is profound. If small bodies can form rings, then the mechanisms of creation and destruction are far more universal than once believed. And if these mechanisms are universal, then the early solar system may have been filled with ringed objects, fleeting, fragile systems that left no trace billions of years later. Chariklo is not just a curiosity. It is a window into the past. Chariklo's rings will not last forever. Every ring system decays with time. Collisions grind particles into dust. Radiation pushes debris outward. Gravity nudges material inward. And in the cold region between Saturn and Uranus, countless unseen forces threaten the delicate balance that holds Chariklo's rings in place. Astronomers estimate that the rings may survive for only a few million years, perhaps less. On planetary timescales, this is brief. Earth's continents have taken longer to drift a few centimeters. Chariklo's rings, shimmering now in the darkness, are temporary jewels. They will fade. They will fall. They will be wiped away by slow, relentless processes of cosmic erosion. Yet their impermanence is part of their beauty. They are rare because they are fragile. They are extraordinary because they are temporary. And they are meaningful because they reveal a universe that is more dynamic, more creative, and more surprising than anyone imagined. In the far future, Chariklo may lose its rings entirely. The particles may fall back onto its surface, leaving no trace of the elegant structures that once encircled it. Or the debris may disperse, disappearing into the depths of space. Without a shepherd moon, if none exist, the rings may slowly unravel, becoming broader and thinner until they are invisible. But even if the rings disappear, the discovery will remain forever. Chariklo forced a shift in scientific thought that cannot be undone. It reshaped the understanding of small bodies. It broadened the known possibilities of gravitational behavior. It opened the door to new searches, new theories, and new discoveries. And it reminded humanity that even in the darkest reaches of space, where sunlight is faint and silence is eternal, miracles can happen. Chariklo, the tiny world with two fragile rings, stands as a symbol of cosmic humility. It shows that the universe does not save its wonders for the giants. It scatters beauty everywhere in places unnoticed, in objects overlooked, in shadows unexamined. For centuries, humanity believed that only massive planets could host rings. Chariklo shattered that belief. It proved that size is not destiny. It proved that complexity can arise anywhere. And it proved that the universe still has the ability to surprise even those who spend their lives studying it. The rings of Chariklo are not grand like Saturn's. They are not bright enough to see through ordinary telescopes. They do not spread across tens of thousands of kilometers. They do not inspire the same immediate awe, but their significance is deeper. They are a reminder that the smallest players can change the rules. They are evidence that creation is not a one-time event, but an ongoing process. And they are a whisper from the outer solar system, saying that there is still much we do not know. Chariklo's rings are impossible but real. They exist in defiance of expectation. They exist in silence. They exist in the cold. And they exist as a testament to the ongoing wonder of the cosmos. The discovery redefined astronomy. The mystery continues to inspire. The universe remains open, waiting, full of unseen miracles. Turriculum may be small, but its impact is vast. Its rings may be thin, but their meaning is profound. And its story unexpected, elegant, and humbling will remain one of the most beautiful chapters in the history of exploration.